So we started section 4.3 last time, and we had talked about this thing called Riemann sums. And if you remember, it's a lot like what we did in section 4.2 with the rectangles under the curve, but the difference is that we let these rectangles get infinitely narrow, right? Their width is going to 0. So there's infinitely many rectangles, and if we do this limiting process enough, it actually becomes something that we call a definite integral. And we had our notation that we're going to see again as we move into section 4.4 later, right here, that defines that in terms of antiderivatives, which we did back in 4.1. So this is the section that starts to pull all these pieces together, okay? We had done geometric arguments for a couple of them. So this one we were just identifying the notation. And then this one we created a rectangle, right? And we found the area of a rectangle, no problem. And this one we created either a trapezoid or a triangle and a rectangle. And we calculated the total for that. And I think that brings us to this last one. Is this one where we left off? I think so. No, we left off at one after this, a couple after this. Okay, so these last theorems. So we talked about the fact that if we switch our limits of integration, we can do that. It just makes the sign in front the opposite sign. And that if we have sort of a stopping spot between the left-hand endpoint and the right-hand endpoint, then it's the same as finding the area over the whole piece. Right? So we find the area for the first piece, find the area for the second piece, add them together, and it's the area for the whole thing. And then this is our last one that we left off on. And it talks about all these sort of expected properties. And not only are they expected, but they pan out. It really works. So when we have a constant multiplier, it just comes along for the ride, just like it did for derivatives and limits. And when we have sums and differences, we just take their pieces individually and we move forward as well. And not only that, but we saw both of these rules happening in section 4.1 as well. So it kind of shouldn't surprise us that just by putting these upper and lower limits that the properties are still the same. So that's a good thing. So the last thing that we're going to take a look at today is the last thing in this section is problems 4 and 5. So we're not finding integrals. We're told what they are. So take a look here. We are being told these 3 integrals values. Okay, they're given to us, they're correct. We'll be able to justify why they're correct in section 4.4. But for right now, we're just taking it for fact. Right, so this is kind of like if you were learning multiplication and somebody says to you 4 times 3 is 12. They don't really argue why it is. They just want you to know it for the purposes of a particular problem. Okay, so that's what's going on here. These are the 3 pieces that were given for this particular problem. They're true, they're justifiable, but that's not our argument for right now. Okay, we're just going to use them. So what we're going to do is we're going to take this definite integral that they're asking us to find, and we're going to use these properties that we've encountered across the last 3 screens, right, to separate it into 3 separate pieces that match up with the stuff in the box. Right? We want it to look like the parts in the box. Notice the limits of integration on everything on this screen have 2 as the lower limit and 4 as the upper limit. Everybody see that? That's important. If they weren't that way, we would not be able to proceed with the problem. Okay, so that's valuable. So what we're going to do is we're going to separate things initially based on property number 2 over here. Property number 2 says if there's addition and subtraction, I can break them apart. Okay? And then also property number 1, which says if there's a constant multiplier, I can pull it out in front. So I'm going to use these 2 properties to separate out problem number 4 into 3 pieces, all 3 of which use one of the things in the box above. So here's what that looks like. We're going to write this as the integral from 2 to 4 of x cubed, and remember, it ends in dx, minus 3x has a 3 as a constant multiplier, so the 3 will come out in front. And then I've got the integral from 2 to 4 of x dx. And then 8's a little funny looking to do this, but remember 8's the same as 8 times 1, right? That's okay. So we're actually going to pull an 8 out in front. Did I get addition instruction? Yeah, I've got it right. Okay, pull the 8 out in front as well. And this is the integral from 2 to 4. And it's really of like 1 dx. And it's important that you realize that up here, there's an understood 1 there as well. It's not a 0, it's a 1. Okay, so when there's nothing written there, the understood value is 1. Just like if there's nothing written in front of x, it's 1x. Okay?
Got it.
Why? Why did we do it? Well, we did it because all of these pieces now, hang on, I'm trying to get just the pieces or the integral pieces, are exactly what's in the box. Exactly. That's our goal. We want to make a very clean and simple, quick substitution that says, okay, well, this first red box looks exactly like the first piece in my outlined black box, right? And so therefore, that value, according to this, is 60, so this part in this first red box is also 60. So I have a 60 right here. And then I have a subtraction sign, and there's a 3. I need to write the 3 down. The second red box also matches up there. What value is the amount in the second red box? It's 6. So this is 3 times 6. And then I have plus my 8. And what value is it in the third red box?
16.
It's a 2, right? And then it's arithmetic. We're doing some multiplication. We're doing some addition, subtraction. What's the end result? What'd you get, Anna? 58? Yeah. Okay, everybody good with that? Okay, remember the whole goal of this whole chapter is we're building things upon itself piece by piece. If you've seen calculus like in high school before, you're probably sitting here and saying, why are we doing it that way? And that's why, is it's building upon it piece by piece. When we get to 4-4, all the pieces that you're remembering from antiderivatives of calculus are going to come out, okay? All right, we have one more. Tell me something about this one that's a little bit different than the last one. Right, the limits are reversed. 2 is now at the top, 4 is at the bottom. Does everybody see that? We cannot proceed forward with this one in exactly the same way as we did the last one, but we do have a property. Where did it go? There it is. It tells us what to do if the limits are reversed, right? It says I can flip them. I just have to put a negative in front when I do. So that's going to be our first step. We're going to flip them. It's going to say 2 to 4, but now it's going to have a negative in front. If you want to multiply the negative through, you certainly could do that. It wouldn't hurt anything. If you want to leave it in front, you can do that, and it won't hurt anything either. Okay, is that step okay? At this point, we're going to do the same thing we did on the last problem. We're going to separate out the 2 pieces. There's only going to be 2 because there's only 2 pieces inside of my integral, right? This is called the integrand. The integrand only has 2 pieces. So I've got a negative in front of the first one, and it's from 2 to 4, and it's x dx.
That's 4 or 2 right there.
What's wrong?
Both of the intervals are 4 to 2.
Both of the integrals are 4 to 2.
4 to 2.
Are you saying from here to here?
Yeah.
I flipped them on purpose with the negative in front. So I do want them to be flipped. I want them to match the ones above. So that's why I did the flipping and put the negative in front. The next piece, you need to use a little caution to be aware of what you're doing. The negative that's in front of this is going to apply to this piece, and it's a negative 7. So I'm pulling out a negative 7 with the negative that's in front actually means I'm going to have a positive 7 here, and then the integral of 1 dx from 2 to 4. If that's tricky to see, then think about what happens when you multiply this back through. This would be negative x plus 7 dx. And you can see the negative being pulled out in front of this one, and then this is a positive 7. Does that make sense?
Yeah.
That sign switch sometimes trips people up. But these pieces now match, just like before. This piece and this piece are exactly what's in the, there's not a box above because I didn't box it in, but in the information above, right? So what is the integral from 2 to 4 of x dx? 6, right? And there's a negative out in front. Plus my 7. And what's the integral from 2 to 4 of 1 dx? 2. So we have negative 6 plus 7 times 2 for a grand total of 8. What do you think? Okay. Glorified substitution is what it is. Identifying pieces that look alike and then making the appropriate substitution.